A transformer is a crucial electrical device that operates on the principle of electromagnetic induction to transfer electrical energy between circuits. It consists of two coils of wire, known as primary coil and secondary coil, usually wound around a laminated iron core. The primary coils are connected to the input voltage source, while the secondary coil is connected to the load. Based on the principle of electromagnetic induction, when an alternating current flows through the primary coil, it creates a changing magnetic field around the coil. According to Faraday's law of electromagnetic induction, this changing magnetic field induces a voltage in the secondary coil. The induced voltage in the secondary coil depends on the rate of change of magnetic flux linking the coil. When the same iron core is used for both primary and secondary winding, the changing magnetic field produced by the primary coils induces a voltage in the secondary coil through mutual induction. Also, the turns ratio between the primary and secondary coils determines whether the transformer steps up or steps down the input voltage. If the secondary coil has more turns than primary winding, then the transformer is step-up transformer. Conversely, if the secondary coil has fewer turns than the primary coil, then the transformer is step-down transformer. The main formula governing the operation of a transformer is V1 times I1 equals to V2 times I2, where V1 is the voltage in the primary coil. I1 is the current flowing through the primary coils. V2 is voltage in the secondary coil. And I2 is the current flowing through the secondary coil. This formula represents the conversion of power in a transformer, stating that the power input to the primary coil, V1 times I1, equals to the power output from the secondary coil, V2 times I2. Additionally, the turns ratio N1 to N2, defined as the ratio of the number of turns in the primary coils N1 to the number of turns in the secondary coil N2, is related to the voltage ratio V1 and V2. N1 over N2 is equal to V1 over V2. Hence, turns ratio determines whether the transformer is steps up or steps down the voltage. Similarly, for a three-phase transformer, consists of a three single-phases transformers combined into a single unit. Like single-phase transformers, the core of a three-phase transformer is typically made of thin, stacked and insulated sheets of silicon steel. These sheets are wound into a three-legged to provide a path for the magnetic flux generated by the windings. In three-phase transformer, there are two sets of windings: primary and secondary windings. Each set consists of three separate windings. For example, 3 primary windings and 3 secondary windings. These windings are typically wound around the core in a concentric manner, or even sandwich manner. The windings are connected in either a delta or Y configuration, depending on the applications. In a delta connection, one end of each winding are connected together in a triangular shape, forming a closed loop. In Y connection, one end of each winding is connected together at a common point, while the other ends are connected in respective phases. Some importance brought about by delta configuration: 1 is simplicity in connection, as connected transformers have fewer winding turns compared to Y-connected transformers for the same voltage ratings, making them compact and less expensive to manufacture. The second importance brought about by delta is higher fault tolerance. Here it can withstand single-phase faults, for example short circuit, in one winding without affecting the other windings, making them suitable for applications where tolerance is important. Delta-connected transformers are commonly used in industrial settings, especially where the load is typically unbalanced and where the system size is relatively small. On the other hand, Y configuration has some advantages, such it provide better voltage regulation due to the neutral connection, which allows for easier balancing of loads between phases. This results in more stable voltage levels. Better insulation coordination, especially for higher voltage systems, as the neutral point provide a reference for the ground and helps in managing transient overvoltages. Transformer suffers several losses through heat, be it eddy current losses or hysteresis losses, hence a cooling oil is used, which sometimes expands, hence the use of tank at the top. Also, bushings are used to lead current into and out of the transformer because of the good insulations. There are two categories of bushings in transformer. For low voltage is called LV bushings, and for high voltage is called HV bushings. But sometimes we need to regulate the voltage output depending on the need. We can do it when the power is on or when the power is off. These are achieved by tap changers. Tap changers is a device in transformer used to regulate output voltage by adjusting the number of turns in the transformer windings. There are two main types, that is OLTC, that is on-load tap changer, and de-energized tap changer. For de-energized tap changers it is quite simple. But for the OLTC it is very complicated as it follows certain steps. And which sides are these tap changers connected in a transformer? Is it primary or secondary side, and why? If you don't want to miss such information, check our next video on transformer tap changers. Also, I take this opportunities to thank all of you who subscribe this channel. It really encourages me to bring more content in this channel. I hope you found this video informative. And if you did, kindly subscribe, like and share. See you in the next one.